Hi guys, in this section we are going to talk about redundancy and resiliency. I know most of the network designer, network engineers use these two terms considering they both are same, they both have the same meaning, and most of the network designers, when even me, when we came up with like increasing resiliency in a network, we basically go and increase the redundancy in the network. It's yeah, that's to some extent that is correct, but we'll try to look more deeper that how these two words or these two terms, what exactly the meaning is. So whenever we think of network resiliency, automatically we think of adding a redundancy. Redundancy does not just impact your resiliency of a network. However, it also impacts your manageability and scalability. So, whenever the next time you increase the redundancy of your network because you want to increase the resiliency of your network, do remember that increasing the redundancy, you are also impacting the manageability and scalability of your network. How? We'll see to it. So, let's move on. Uh, Yeah. So, how your redundancy actually increases your resiliency, that should be pretty much straightforward, but we'll look into it. For example, we have two routers, router A and router B, connected via single link, and we have LAN networks behind A and B. So, this is a pure single link, single router kind of technology. So if, for example, we need to increase the resiliency, what is the first thing which we are going to do is we are going to increase a parallel links connecting between router A and router B. So by this way, we have basically increased the resiliency by adding a redundant link. So a single link failure will not result in the loss of connectivity between the two hosts. Although this prevents the single link failure from causing a network disruptions, it leaves router A and router B as a single point of failure. If either one of them is fails, your entire network will fail. So we have added a redundant link between them. Now imagine increasing a link, what we have avoid. We have avoid a single point of failure. Now what happened? If still we have a dependency on a router, that means any of the routers can fail. So your dual links cannot fulfill your purpose. Even if you have two links, if any of router A or router B fails, your network will be down. So if you want to increase resiliency more, what the next you can do is you can just go and just a minute, you can go and say, okay, I'll have a dual routers, and instead of these two links, dual links, I can have single links and dual router kind of scenario. So what basically you did is you have increased your resiliency to one level more by providing a redundant router so that you avoid that single point of failure. So you'll be having router A, router B, router C, and router D. So in this way, you have four routers connecting this way. This will be your LAN, this will be kind of your WAN scenario. So what happened is the additional router increased network resiliency by providing a backup for router A and router B. In this network, a single link can fail with no impact. If even above the link between A and B fails, there will be no impact. A single router can fail with no network impact, or a pair of routers, do remember, as long as they are both attached to a same link, can fail. However, if one of the router fails on each link, that means if router B and C fails, the network will fail. So therefore, although this network has no single point of failure, it has a double point of failure. So resolving all of the double point of failures would involve adding a third router at both of the sides. Hold on a second. Are we really looking at this way? That if we want to increase the resiliency, so do we need to add a third router? Also, we can have resolve the same failure by adding another pair of links. So we can say, okay, instead of adding pair of routers, we can have a pair of links installed. So in this way, what exactly we are doing is we are increasing the redundancy because we want to increase the resiliency. So redundancy goes with your resiliency. The more resiliency or the more level of resiliency you need in a network, the more redundant you need to make your network. So after the links between router A and router D and router B and router C are added, any pair of links between the routers can fail, or any one router and any one link or some pair of routers can fail, and the network will still be capable of passing the traffic. So this is what basically you can go with, find of different signal. So imagine how then you determine how much redundancy to build into a network to provide a given amount of resiliency. Because this really sounds okay from a low level designer perspective. If you think, you say, I have a requirement to add two routers, two links with interchange, like this kind of scenario. So you basically won't go much into the detail of what level of redundancy you need to provide, because you have a requirement from a high level that we need this kind of redundancy. But imagine from a high level perspective, when someone talk to the customer to understand their business needs, he needs to translate that into a network needs, that how much redundancy should be there to fulfill what the customer resiliency requirement is. Also, customer is not going to tell you the resiliency requirement in terms of technical language. It will be moreover kind of a business language, and you need to understand the level of resiliency. Accordingly, you can decide the redundancy level. So the method described so far is analyzing the points of failure in the network and comparing this to the number of failures that the network should be able to resist at any point. It's the common way of determining the amount of redundancy required at each point. For example, if you determine that a single equipment or a link failure should not cause the network to fail, you need to eliminate all single points of failure in a network. If you decide that any two failures should not cause the network to fail, you need to examine the network from a point where double point of failure exists and determine how to avoid them. There is altogether a very big statistical analysis, which I'm not going to discuss here because that really needs a lot of deep understanding of things like mean time between failure, mean time to repair a network, mean time between failure of your component, mean time between failure of your systems. According to that, basically a high level network designer or an architect decides that how much redundancy should be there in your network. That really needs a lot of information to gather out, put it into the formulas, and then calculate and come up with the final resolutions. Okay, this much redundancy we need because this much resiliency we need it out. So this, so till now we understood like redundancy goes hands in hands with your resiliency. The more resiliency you need, the more redundant you need to make your network. But as we discussed, redundancy is to increase your redundancy. It's not just increase your resiliency, it plays with your management complexity as well. So redundancy increase your management complexity. So far, we have learned how redundancy can improve the resiliency of a network. So in this, we say how your redundancy increase your management complexity. There are basically three elements to be considered. First, called a 2 o'clock morning test. In the network terminology, this means like the ability to configure a network, otherwise known as which is 2 o'clock. If someone who is unfamiliar with your network works on it at 2 o'clock in the morning, he might be very sleepy. Obviously, it's 2 o'clock. Will that person be able to understand the configurations and why they are there? This is called a management complexity. Second, the ability to monitor the network. Third, the ability to troubleshoot the network when a failure occurs. These are the three very basic functions which comes from the manageability perspective. As the redundancy is increased, the difficulty of each of these management functions increases. For instance, when you are attempting to configure the network, a set of 5, 10, or 15 possible parallel paths through multiple intermediate devices can make it too difficult to understand what the traffic flow should look like and to configure the devices to achieve the desired traffic flow. Because if you the more parallel links you have, the more and more options you have for your traffic flow. So you should be, or the person who is configuring the network should have a proper understanding of what should be the traffic flow. Troubleshooting a highly complex redundancy scheme can also be difficult. Which direction should traffic be flowing? In a transit loop across 10 paths normal, or is it a symptom of a network failure you're working on? So it's really your troubleshooting complexity will increase as your redundancy increases. One of the most useful tactics that an engineer has when beginning to work on a network failing to converge is to remove the redundancy until the network converges. So this sounds good. If you want your network is not converging properly, remove the redundancy and then see how your network is converging. After the network stabilize, perform a postmortem of it, determine what happened and how to prevent from happening again. Although management complexity is difficult to measure, experience indicates that two parallel paths is optimum balance between the management complexity and a good resiliency. This you can't have a thumb rule like two parallel paths or three parallel paths. Again, these things depends upon your resiliency. How much resiliency you need it, you will place the redundancy, but you will have to deal with the management complexity. Not only management complexity, you need to work on your scalability. Redundancy can reduce your scalability. There's a trade-off that the network engineer makes when increasing redundancy in a network is between your resiliency and scaling. So each additional path added to their network can decrease the speed of convergence in the network. If you consider the job of routing protocol and how routing protocols operate, this makes sense. The more paths that a routing protocol must examine before determining the best path to a destination, the longer it is going to take to determine the best paths. Again, this is often too difficult to quantify because your routing protocol normally when it converge, it depends upon how many different paths it needs to take into an account. So you can see that the convergence time increases as the number of routes increases, as you would expect in all routing protocol. So as the number of paths available increases, the convergence time also increases. So the question is, will do read this question properly. Will the network experience more total downtime because of the increased convergence time with more parallel links, or will it experience less downtime because of the decreased downtime involved with having more links? Huh, this looks really like confusing. Oh, what is this? Do read it in two separate ways, before or and after or, because there are two situations. Because if you have parallel links and if you don't have parallel links, you need to understand from the protocol convergence point of view that if your link flaps, how much time your network takes to converge for the second parallel links. Will that be less? Or when you don't have a parallel link and your links come back up, how much time your network take convergence before if you have a parallel link? So you need to kind of a trade-off like, oh, if your network convergence is really high from a flapped link, so it's better that it should be flapped other than from the parallel path. So the answer depends on the frequency of link failure, the amount of time required to restore a failed link, the number of routes in the network, the number of times the network convergence on a given route, and blah blah blah. There are many other factors which might need to be taken into considerations. So the answer is not straightforward. In most situations, However, adding a third parallel link tips the scale against the higher resiliency because of the increased convergence time with few gains in link uptime. To know for certain, you will need to calculate the uptime rates and the convergence time and then compute total uptime based on the number of convergence events versus the number of link failure. So it's like you need to take an action because do remember in designing, you can't have a thumb rule for each and everything. You need to understand, you need to take an account of various aspects, but because you should know various aspects so that you can take an account of it. Another point which you can consider is like your additional memory and processing requirements. Whenever you add links, the route of memory and processing time required when it depends upon you are running a distance vector protocol or your open shortest path first kind of link state protocol. So this was all about your redundancy, which is depends which affects your resiliency, manageability, and your scalability of your network. I hope this section gives you some good view of redundancy and resiliency. Thank you very much, and we'll see you later.